like that. Okay, so guys, this is what we're up to today. Here's the promise that I make to you. You ready? Guys, this is all of your notes for today, assuming that you learned something in the flame test lab that we did last time. Remember, that's due on Monday. You can turn it in early if you want. But here's the way this is going to go. As we are talking about really hard things today, this is all the stuff you need to write down. So if it ain't on here, if it's not on here, but it is on here, it doesn't need to be in your notes, because if it's up here and on here, write it down and otherwise let it go. But guys, with that said, what we're going to do is we're going to start by revisiting the flame test lab. So you may want to flip this over just to give you a little bit of space so that you can write down things relative to the flame test lab. First period, I didn't think to mention that. And then as we started talking about the flame test lab, a lot of my kids had no idea what was going on. And so I said, if you don't know what's going on, flip your paper over, which immediately meant if you flipped your paper over, you were stupid, right? Because you don't understand the flame test lab. So why don't we all just flip our paper over, then we can be equally out there as stupid people, and you can write down the notes that you need, not drawing attention to what you don't know. Okay, so guys, this is where we are. You ready? We are on a journey. And guys, I know we've talked about this before, but it's critical that you understand the journey. This you don't need to write down. So guys, the journey has gone from Dalton to Thomson to Rutherford. Hey, we got the nucleus of the atom. The electrons are all mushed around, and we know that's not right. So then we come down here to Bohr, and we understand the Bohr model of the atom to be the planetary model of the atom. But guys, why did we build up the Bohr model of the atom? To tear it down, right? We talked about the idea of a straw man, a concept that we're going to build up just to tear down. But guys, you've got to understand the work that we did during the lab on Tuesday to understand how we can build this up to tear it down. So guys, when we did the lab on Tuesday, which for some of you has been your favorite lab so far, and probably the only thing you're going to remember in this class next year, because you got to put Q-tips in fire and make pretty colors. But guys, the question is this: why on earth did we put the stupid Q-tips in the fire? And it was not to make pretty colors. It did make pretty colors. But guys, what on earth do pretty colors have to do with electron structure? What's the connection? And if you can't answer this, you didn't understand what happened in the lab last time, and you probably got all the conclusion questions wrong, and you'd better write it down. So, what's the connection between pretty colors and electrons? Don't be scared. Go ahead, Ethan. Good. Keep going. And what do the wavelengths tell us?
The wavelengths tell us by using a high energy photon.
Good. So look at the connection, and there's a lot of links. The pretty colors tell us the wavelengths. The wavelengths tell us the energy. What does the energy tell us? How far the electron fell. Right? Guys, you've got to understand that. If you want the refresher, feel free to write it in your notes. But starting with Ethan and then tying together with these guys back here, the big idea is this. Bohr studied light, pretty colors. Why did he study pretty colors? Because these colors tell us the wavelength, and the wavelength tells us the energy, and the energy tells us how far the electrons fell. And so the big encompassing idea is that by knowing how far the electrons fell, you can figure out how the electrons are organized around the nucleus, and that gives us the electron structure of the atoms. And by doing that, Bohr figured out that the electrons were in orbits and not all gobbledygooked, not all plum puddinged around the nucleus like Thomson and then Rutherford thought to be the case. So the idea here, guys, is by studying that light, we figured out that the electrons were falling through distances. By knowing the distances, we could figure out the structure, and that's how we got here. Yeah? You okay? You're good? You're really, guys, you got to make anything you want to talk about there. You're okay? Okay. So here's where we are then, guys. Is this really what an atom looks like? No. But you got to get comfortable with this. Is this right? No. There's a line through it. But is it completely wrong? No. So guys, here's what we're going to do today. We are going to talk today about, first of all, why this is wrong. Then we're going to pick up the couple of pieces out of the pile. So we're going to take the Bohr model and we're going to shatter it and throw it on the floor. Then we're going to reach down here and we're going to pick up those couple of pieces that are worth hanging on to. And we're going to take those and use them for the foundation of this model. Now guys, here's the trick. This model is actually built on the Bohr model. You can kind of see, if you look at this from a distance, there are still like some ring-like structures there. You especially see it here. There are some ring-like structures even in the Schroedinger model of the atom. Of course, it's not as simple as this, but there are still some ring-like structures. So we're going to make the connection between the old and the new, but we are not going to go fully here until Monday. You get the idea? Okay, so guys, with that said then, this is how this is going to roll out. And this is not on your paper, so don't write it down. But guys, it's critical that you understand our goals today. First thing we're going to do is we're going to bustamify the Bohr model. We're going to talk about why it's not complete. Then what we're going to do is we're going to gather together the information that we need to make the big jump on Monday, but we're not going to build the new model. We're only going to collect the building blocks. Do you understand the limits of what we're doing? Then let's get started. So guys, first of all, the Bohr model of the atom. Notice this isn't in your notes because you probably wrote this down on the back of your paper. So here's what we know. Bohr developed his model by studying the light that is released by falling electrons. Now, in order to do this, in order to describe electrons, and this is what Bohr was trying to do, in order to create this model of electrons falling, you've got to treat electrons as if they are little particles revolving around the nucleus. So you ready, guys? Make the connection. Imagine that this is the nucleus of an atom. And guys, none of this is on your note sheet, so you don't need to write it down. You already know this stuff. So here's the idea. Watch my fist. That's the nucleus. Okay, now it's gone. It's still there. I just can't do this because I can't wrap my hand around my arm. Okay, so here's the nucleus, and this electron is going like this, and this is the Bohr model of the atom, and it's in its lowest energy state, which we call what? Ground state. And then we want to kick it up to an excited state. So what do we have to add? Energy. What kind? Doesn't matter. Boop. Now it's in an, I'm going to hit this table. Now it's in an excited state. Does it want to stay there while my fingers fill up with blood? Does it want to stay there? No. Back down, and when it does, it releases light, right? Now guys, obviously this entire model requires that we describe these electrons like particles moving around the nucleus, like planets moving around the sun. That's why we call it the planetary model of the atom. And guys, that worked for a while. So as Bohr developed this model depends on the ability to figure out where an electron is and where it's going, to locate it and track it in space so that you can figure out the paths of its orbits. So as Bohr was developing this model, what he did is this. He used a single variable. Just remember the letter n. He created this single variable that describes the size of the orbit. So here's the nucleus of an atom, and this first orbit, which he called n is equal to 1, was that first smallest orbit. Then, as he's exciting electrons, he found out that there were other bigger orbits, like layers around an onion, and each successive bigger orbit, he just gave a number, 1, 2, 3, and on out to the edge. You understand the idea behind the Bohr model? You're okay? Okay, now this is where you need to start taking notes. Because guys, this is where things get weird. You ready? Because here's what happens. So Bohr is developing this model of the planetary model of the atom. He's tracking these electrons electrons around the nucleus by exciting them and watching them fall. And guys, all of a sudden, after about 6 months to a year of this research, things just blew apart. Not literally, but things just went horribly wrong. Bohr was gathering all of this data from the lines and the light and all this other stuff, and all of a sudden his data was just garbage. He sat down to analyze his data, and none of his data made any sense at all. It was just broken. So what's the first thing he did? He repeated his experiments, and he got the same broken data. So guys, what does a scientist do when they get data that doesn't make any sense? What do you do as a scientist when that happens? You publish it. You send it out to all of your scientist friends, and you go, hey guys, look what I'm learning, and this doesn't make any stinking sense at all, so why don't you look at it and help me understand it, because I can't figure it out. First of all, you make sure your data is not flawed because you're doing something wrong. But as soon as he knew that his data was good, he published it. And guys, it turns out that his data fell into the hands, and this is the first thing in your notes, fell into the hands of a dude named Heisenberg. And Heisenberg grabbed a hold of Bohr's data, and you may remember this from the video where the guy in the video talked about Heisenberg's wicked math chops. I don't know if you caught that. Guys, Heisenberg was a frighteningly good mathematician. And Heisenberg grabbed a hold of Bohr's data and started to analyze it, and he found something fundamentally crazy going on in Bohr's data. And the idea is this. So Bohr model of the atom, right? Electrons are like little planets. In order to develop that model, you have to know where this electron is and where this electron is going all the time. And as Heisenberg was looking at Bohr's data, he figured out something really disturbing. It's impossible to know that. And it's called the Heisenberg Uncertainty Principle. What does it mean to be uncertain? What does that mean? You just don't know, right? And guys, that's the Heisenberg Uncertainty Principle. It says this. It says we can't know exactly where an electron is and where it's going. So this whole time, Bohr is developing this model of the atom that relies upon our ability to figure out where they are and where they're going. And then his experiments go haywire. His data can't be understood. Heisenberg grabs his data, starts analyzing it mathematically, and goes, wait a minute, there's a problem. You can't do that. You can't know where an electron is and where it's going. And so the first thing that they thought was that the data was bad. But then they went back and they looked at it, and it turns out that the problem was not with the experiment. The problem was with the electron itself. And guys, this is where this gets crazy. See, it turns out that there is something fundamentally unusual about electrons that don't allow you to study them in such a way that you can figure out where they are and where they're going. By the way, guys, you already know what that thing is about electrons that doesn't let you do this. What is it about electrons that doesn't let you figure out where they are and where they're going? They aren't particles at all. What are they? Waves. See, that was the tricky bit. The whole Bohr model of the atom requires that you study electrons as particles. It fell apart. Heisenberg analyzed the data and said, oh, that's the problem. You can't even know where they are and where they're going. And so their first response was, well, maybe our experiments are no good, and if we did better experiments, we could figure out where they are and where they're going. But through further thinking and experimentation in math, they came back and said, no, it'll never work. You can never figure out where an electron is and where it's going because electrons fundamentally can't be studied that way. And the whole Bohr model fell apart. You guys okay? You with me? So here's where we are. Bohr model of the atom treat electrons like little particles. All of a sudden it started to not be successful. Bohr publishes his data. Heisenberg sees his data, says this is never going to work because you can never know where an electron is and where it's going. They said, wait, is it just because our experiments aren't good enough? They came back later and said, no, it's because there's something fundamental about an electron that won't let you know where they are and where they're going. They're tricky little buggers. We will always be uncertain about where they are and where they go, not because we're not good at tracking them, but because they're untrackable. You get the idea? All right. So what happens next? Well, along comes our good friend Erwin Schrödinger. See where you have the word probability? Write Schrödinger next to that. This was Schrödinger's big moment. We're going to watch a video about Schrödinger in actually about 6 weeks, and you're going to find out that Schrödinger was a slimy dude. He was married, and actually some of the best physics research that he did was while he was hanging out with his girlfriends in Europe. He was sleeping his way across Europe. He was a really scuzzy guy, but he was a really good chemist. So guys, it turns out that Schrödinger, in addition to being a slimy guy, also was a really, really bright, insightful thinker. And here's what he did. He said, all right, I've been looking at this Bohr model, trying to treat electrons like particles, and I'm starting to understand because of Heisenberg that can't work. And so we need to come up with a whole new way to think about atoms. Now listen, guys, because this is subtle. You ready? If you're Bohr trying to study electrons like little particles, you need to know exactly where they are and exactly where they're going all the time. Heisenberg said that's impossible. So here's what Schrödinger did. He said, if we can't do that, what if we expand our thinking a little bit? And what if instead of needing to know exactly where they are all of the time, listen close, instead of knowing exactly where they are all the time, what if we just allow ourselves to know where they will probably be, get the connection, probably be most of the time? And so Schrödinger proposed the idea of probability. Guys, probability simply describes your ability to know where an electron will be most of the time. Heisenberg said we can never know where they will be all the time perfectly, and if we do know where they are, we don't know where they're going. So, what if we allow ourselves the freedom to say, let's talk about where they probably will be most of the time? And so Schrödinger proposed this idea of electron probability. And as he started to think more about it, don't write this down, he started to create plots that look like this. So guys, take a gander at this with me, and let's make sure you really understand what you're looking at. So what is the heavy dot? Obviously, I drew that myself. What does the heavy dot represent in the middle of the circle? What's in the middle of an atom? The nucleus, right? Okay, so what do all the blue dots all throughout the rest of the picture, what do they represent? Not electrons. What do they represent? One electron. Do you get it? Okay, so here's the idea. All of those dots represent one electron. What is that one electron doing? It is moving randomly around the nucleus through these wave-like patterns. And as that electron moves randomly through wave-like patterns around the nucleus, imagine that it's leaving a trail behind it. Is the best example I can come up with, and this is actually kind of weird, but bear with me. So I have a dog, I have a lab, and in the winter, see my dog, he's a creature of habit. He gets up in the morning, he eats breakfast, and then he goes outside and poops in exactly the same place every day. So when it's a cold winter, well, a snowy winter day, and our backyard is full of fresh snow, I let my dog out in the morning, he goes out, poops in the same place, and comes back in. But if you actually go out on my deck and look, you can see see that he's sort of wandering around in circles, and every time his foot goes down, he leaves a mark, right? So if I were to look at that from above, I can tell where my dog was because he's leaving tracks in the snow as he sort of circles around, poops, then circles around and comes. Do you get the idea? So my dog leaves tracks in the snow. In the same way, these electrons can be thought of as leaving tracks in space. And each one of these dots, and obviously this should be three-dimensional, but each one of these dots represents the place where the electron's been. You get the idea? So if you're still unclear, let me offer it to you this way. Ready? Let's turn this off and grab a strobe light. Okay, so it goes like this. Let's speed that up just a little. There we go. Okay, so electron, strobe light, and then I'm going to just borrow your desk here for a second. You don't need to move or anything, but just for illustration's sake. Okay, so the illustration goes like this. Guys, imagine that the desk is a piece of film, okay? And every time the light flashes, it exposes the film. You get the idea? So if we put electron here, the electron will cast a shadow on the film, and if we were to develop the film, it would leave a dot. Get it? Kind of like the dots that we saw previously on the screen. Now, if the Bohr model of the atom was correct, and if this electron is going like this, and every time the light flashes, it leaves a dot. Guys, if we were looking at the Bohr model of an atom, what would the film look like? A circle. Do you get the idea? So the tracks would be a perfect circle, the electron just moving through an orbit, planetary model, Bohr model. You get the idea? Okay, but that's not what electrons are doing. Electrons are going moving all over the place through these wave-like spaces. Now, if we were to do that, and if we were to develop the film, what would the film look like? The film would look like this. Do you get the idea now? So that's what we're looking at. We are looking at the dots that are left as the electron is moving randomly around the nucleus, and each one of those dots represents a place where the electron was or someday will be. You get the idea? You're okay? It's critical you understand that. Okay. So guys, with that as a background then, here's the idea. What if we allowed this to continue to play? What if we did this for hours or days or weeks or years or whatever, but for a long period of time? Eventually, what would this picture look like? What would it look like? It would look like a solid. Now, does that mean that an electron is a big old huge solid? No, but guys, when we describe electrons in the Schroedinger model, the correct model, when we describe electrons in the Schroedinger model, we don't treat them as points moving around in an orbit. We treat them as if they are these big old solid clouds that are actually a representation of all the places the electron can be. Do you get the idea? But guys, again, let's make sure you're clear. What does this big old solid cloud actually represent? One electron. So hold on a second. You're telling me that this one electron behaves like it's a big old solid? That's exactly what I'm telling you. Guys, this one electron, because of how it moves randomly and very quickly around the nucleus, behaves as if it's a big old solid when in fact it's just one little itty-bitty point in space. Now, guys, remember what we talked about before when we said that atoms are mostly space? Remember that? If the atom is the size of a marble, how big is the electron cloud? Lavelle Edwards Stadium, right? But it's just one electron. Atoms are mostly space. Now we can pull those ideas together. Yes, an atom is mostly empty space because the nucleus, if it's the size of a marble, the atom is the size of a football. stadium. And guys, all of the rest of that is empty space. So if atoms are mostly empty space, and if we're made of atoms, why are we solid? Why is this solid? And the answer is because these electrons moving so rapidly around the nucleus appear to occupy these solid shapes that behave as if they're solid, even though in fact they're not. So hold on. You're telling me that an electron is not a particle moving around the nucleus like a planet. It is a wave moving randomly around the nucleus in all sorts of crazy directions. And when we think about it that way, we now think about the electron behaving as if it's a big old solid cloud, even though it's an individual point. And the answer is yes. But guys, here's the thing. It sounds crazy, right? But I would propose to you that it's not actually that foreign of an idea. This whole idea of things appearing to be solid when they're really not is really not that big of a stretch. Because I would propose to you that that is exactly the same thing that a fan does. Watch. Okay, so we're going to let this fan be our atom. So if this fan is our atom, what is the middle? The nucleus. And what do the fan blades represent? Electrons. Now, if this thing were built to scale, if the middle was the size of a marble, how big would the blades be? Level-word stadium. Not built to scale. But here's the deal. I'm pretty sure I'm going to get electrocuted, but let's see how this goes. All right. So guys, here's the idea that we're exploring right now. We are exploring this seemingly nutty idea that an individual electron, because it moves through a very rapid wave-like shape, can behave as if it's a big old solid when in fact it's really just one point in space. Well guys, fans are the same way. Watch. So I think you would all agree that there is space between these blades, right? And I can demonstrate that to you, even though I'm proving to be really bad at this. But I can actually shoot, oh, that was good. I can actually shoot rubber bands right through the spaces between the blades, right? You can see the spaces. Now watch, oops. Now watch what happens. Turn this on. Uh-oh. Where'd the spaces go? Are they still there? But do you see how it kind of looks like a cloud? And guys, here's the thing that's crazy. Not only does it look like a cloud, it behaves as a solid. Watch. When I try to pass rubber bands through it now, oh, I missed. When I try to pass rubber bands through it now, oh, poop, that shouldn't have happened. Oh no! That's awesome. Come on, baby. There we go. Okay, you get the idea. And okay, so it's not moving as fast as an electron, but there we go. So guys, now when you try to pass electron or try to pass, no way! I've never gotten, well, 2 in a row. Now I've got, there we go. Okay, but you get the idea that this thing is now behaving, oh, I was too low, behaving as if it's a solid, even though, no way. All right, I'm speeding it up. We're doing this over. That's bugging me. Now it'll work. We just need more speed. If I shoot through one now, I quit. All right, let's see what happens. There we go. Oh. That one ricocheted. All right, so now guys, oh, that's what we're after. Now it's behaving as if it's a solid simply because the fan blades are moving, right? You get the idea? Now guys, electrons do the same thing. Because they're moving around the nucleus, they also behave as if they're a solid, even though in fact they're mostly empty space. So here's the question. Is there really still space between the fan blades? Let me prove it to you. See the space? Look, there's a space right Ow, no, ah! Hold on, wait. I see it. Because there's space there. There's got to be space there, right? I saw the space. So look, there's space right. Ah, hold on. No, hold on. There's space there. Look, you can see the space. But guys, if there's space there, why can't I get my stupid finger through the space? Because it's moving. So guys, this is not a foreign concept that things with space can behave as if they're solid simply because they're moving. Do you understand the idea? Now guys, how does the strobe light work? This has nothing to do with electrons. But here's the idea. So guys, what's happening is that the strobe light is flashing at exactly the same, well, not exactly, it's moving a little. Let me see if I can get it better. So the strobe light is flashing at the same speed that the fan is spinning. And as a result, the blades are only illuminated every time the fan goes through a revolution, and therefore it appears as if the blade is stationary. Now, you ready for a little musical moment? This is the first harmonic. This is the second harmonic. This is the third harmonic. And oh, I can't get there. I can't get to the fourth harmonic. But the idea is that the second and third harmonics are then illuminating it 2 and 3 times per revolution, and it still freezes it in space. But we go back to the simplest first harmonic, and that's what we were looking at before. You get the idea? So guys, bottom line, we now are more comfortable with the idea that something that actually has empty space can behave as a solid simply because it's in motion. And when we're talking about electrons, they don't spin around the nucleus like fan blades. They move through these wave-like spaces that then create clouds that look like that. You get the idea? You're good. All right, so let's get this stuff out of the way. So Mr. Miller last year, I don't know if any of you knew him, he actually was doing this with his classes and stuck his finger in from the back. See, I'm smart enough to know that it's spinning in this direction, and so when my finger hits it, it just slaps it, right? It still kind of hurts, but he stuck his finger in from the back, and instead of slap, you get slice. Yeah, not quite so fun. Okay, so. Okay. So, guys, here's where we are then. Yeah, go ahead.
So, it's not like the electron. Electron doesn't have to be an electron cloud. It's just most likely.
Exactly, and that's what we're going to talk about now. So, guys, no, Matt brings up a really good point, though, guys. Understand that when we describe these electrons as existing inside of these clouds, understand that's just where they probably will be most of the time. They can be outside of that space. They just don't spend a lot of time there, so we describe them as being inside these kinds of spaces. Okay, so with that said, guys, this is the last of what you need to write down under probability. So the idea of probability treats electrons as if they occupy the entire space, rather than treating them as if they are points along a path. Now, guys, along the way, we gave these spaces names, and this is a word that you've heard before. We don't just call these spaces electron clouds. The term that we are going to use is orbitals. Oh, I heard that in the videos. Yep. Guys, these clouds, these spaces, are what we call orbitals. Not orbits, but orbitals. You guys good? Y'all caught up? You okay? Okay, so guys, it's at this point that you want to take a deep breath. It's over. We have now killed the Bohr model. The Bohr model's laying down here in pieces. We understand that it doesn't work. We understand that it was Heisenberg that first proposed why it didn't work, simply based upon the idea that you can't treat electrons like particles. Why not? Because they're not particles. They are wave-like things traveling around the nucleus, occupying spaces that are better described as being clouds. Now, from there, what we now need to do is sort of give you a little flavor for how crazy this gets. You don't need to write this down. But guys, it turns out that not only are these orbitals more like clouds, but most of them aren't even spherical. For example, this. Guys, this is a neon atom. And in a neon atom, you actually have 5 clouds. You have 5 orbitals. Let me help you see them. There is an orbital right here. It is the smallest of the orbitals, and it's located like the rest of them around the nucleus. Then guys, the second orbital, which is also a sphere, is right here, and it's a little bit bigger than the smaller orbital that's inside it. Then guys, there's another orbital that's right here, and it's not even spherical in shape. It's a figure 8, or we will call it a dumbbell shape, and it looks like this. And then there's another one right here, and then there's another one right here. So we have 1, 2, 3, 4, 5 orbitals, and each of these orbitals holds 2 electrons for a total of 10 electrons, and that makes this neon. This is what a neon atom actually looks like. Not quite the Bohr model. You okay, Matt? Okay, are you okay? So, guys, here's the thing. That was just a little taste of Monday. I just wanted to lay that out there so that you understand that while, yes, these spaces do exist, they're not all spheres. But understand, guys, that these electrons are not moving like this. They are actually waves that take on these shapes, and these things actually behave as if they are solid. They push on each other. They interact with the world like little arms when they form bonds. Guys, this is what these atoms actually look like. So, guys, we are now ready to put Bohr in the grave. You ready? You've got this table in front of you, Bohr on the left, Schrodinger on the right. It's time to finally leave Bohr behind and move ahead to Schrodinger. And it goes like this. So what's wrong with Bohr? Was he completely wrong? No. But where was he off? It goes like this. So guys, the problem is that Bohr's model was inappropriately two-dimensional. See, Bohr was treating electrons and atoms like solar systems. And guys, our solar system is flat. And atoms are not flat. They're three-dimensional. See, this three-dimensional nature is important because 2D is just too simple. A three-dimensional structure is appropriately complex. See, guys, and that becomes important because we find out that no, atoms are actually not like solar systems. They don't obey Newtonian physical laws. They are not like solar systems. Instead, they are systems of electron clouds. And when we talk about electron clouds, we no longer talk about orbits. What do we talk about? Orbitals. See, guys, the reason that is important is this. When you talk about an orbit, you talk about a path. But when you talk about an orbital, you talk about another word that begins with P. It's not a path, it's a probability. Right, there you go. So, what then can we salvage from the Bohr model? And guys, the answer is N. Remember when we started talking today and we said that n is the size of the orbit? Well, it turns out that when we start talking about orbitals, they also have sizes. Like you saw in that neon atom, some of the orbitals are small, some of them are big. So when we talk about Schrodinger's understanding of this, we are still going to call the size of the orbital n. But here's the problem. Not all the orbitals are the same. Some of them are spheres, some of them are dumbbells, some of them look like clover leaves, some of them look like snowmen. Guys, this gets crazy. So we need more variables to describe the craziness. We needed 3 more variables. So they kept n and they brought in L, M, and S. Okay. So guys, now we're ready to tee up the ball for Monday. You ready? Guys, you see this down here? See this outline that I gave you? Here's what we're going to do for the next 7 minutes, and then we're done for the day. We are going to fill out this outline. Let me help you get started. You ready? N, L, M, and S, right? Do this with me. All you're doing is filling in the blanks. I couldn't make this any easier for you. Well, I could have filled in the blanks for you. Okay, so notice the 4 black dots, right? Those are the 4 major topics. The first major topic is the principal quantum number. That's n. Write it in the space. Now go down to the next major topic, the subprincipal quantum number. That's L, the next one that you wrote in the box. Then the third one is the orbital quantum number. That is M. And then the final quantum number is S. That is spin. That is the spin quantum number. Now, guys, here's what's going to happen for the next 7 minutes. You are going to feel like you've been beaten by words. We are just going to fill in all these spaces. And you're going to be going, okay, stop, I give. That's enough. 7 minutes. Hang in there. You'll be fine. But guys, here's what's going to happen. I'm going to give you all the information that's required to fill in these boxes. Some of the things I'm going to explain to you. Some of them I'm just going to take as fact and just give them to you. But then, guys, here's the deal. On Monday, this outline right here, guys, describes this. This outline is this. And that's what we're going to do on Monday. We're going to make the connection between this outline and that. And guys, I promise you, it sounds corny, but it's magic. It's really crazy how these connect. Now, here's the thing, just really quickly. If you have not yet purchased one of these periodic tables, you've got to have one of these by Monday or you're sunk. Get one by Monday. Okay, so guys, with that said, we're going to fill out the rest of this outline. You ready? Goes like this. What we are doing is identifying these values for what are called the quantum numbers. So guys, let me just lay this out for you right now. Ready? Think about Schrodinger. What experiment did Schrodinger do to come up with this? He didn't. He did math, right? And when you do math, in your equations, there are variables, right? Like x and y. Except for in his equations, the variables weren't x and y. Guess what they were? N, L, M, and S. Guys, N, L, M, and S are the variables in Schrodinger's equations. So you ready? If you plug in just the right variables, and I'll tell you what they are. If you plug in 1 for L, 0 for M, 1 for N, 0 for L, 0 for M, and plus 1/2 for S, and you graph it, guess what you get? A small sphere. If you plug in 2 for N, these aren't numbers you need to know, 2 for N, 0 for L, 0 for M, and plus 1/2 for S, guess what you get? A bigger sphere. If you plug in, got to think about this, 2 for N, 1 for L, -1 for M, and plus 1/2 for S, and you graph it, guess what you get? A figure 8 that goes up and down. If you change M to 0, you get a figure 8 that goes left and right. And if you change M to plus 1, you get a figure 8 that goes in and out of the paper. So these N, L, M, and S values are the values in Schrodinger's equations that helped him figure out these shapes. Crazy, right? But here's what you need to know about them. Join me at the board. So guys, the principal quantum number tells us the size of the cloud, the size of the energy level. Now, how many different sized clouds can there be? 7. The values on the periodic table range from 1 to 7. Now, this is the first thing that you need to understand. It's called the 2n squared rule. Guys, the 2n squared rule tells us the number of electrons in an energy level. So here's the deal, guys. You're going to want to write this down with me. You got a little bit of space right here, right? On your paper. Write this down. So the energy levels go 1, 2, 3, 4, 5, 6, 7. Now, how many electrons, what is the capacity? How many electrons can go in the first energy level? Well, guys, plug in 1 for n. What is 1 squared? 1 times 2? 2. 2 electrons can go in the first energy level. How many electrons go in the second energy level? Well, plug in 2. What's 2 squared? 4 times 2 is 8. How many can go in the third energy level? Plug in 3. 3 squared is 9 times 2 is 18. How many can go in the fourth energy level? 4 squared is 16. Double that is 32. How many go in the fifth energy level? 50. If you can't figure that out, you don't know the pattern. How many can go in the sixth energy level? 6 squared, 36. Double it is 72. And then finally, 7 squared is 49. Double that is 98. That's how many electrons can go in the energy levels. Okay. Now, these energy levels, again, being described by n, change as you go up. So, as n increases, 3 different things increase. The first one is size. You already knew that. We said the n describes the size and it gets bigger. Guess what else goes up? The energy. But you already knew that. How did you know that? How did you know that as n goes up, the energy goes up? What? I heard the lab, guys. Good for you, Josh. The flame test lab. That's what you were doing in lab. You were taking an electron in energy level 1, adding energy to it. If it went up to energy level 2 and then fell back down, it released energy in the form of light, probably red light. If you took an electron from energy level 1 and kicked it up to 5 and then it fell down, it was probably blue light. So guys, this is evidenced by the flame test lab. And then finally this, the capacity goes up. How do you know the capacity goes up? That's the 2n squared rule. That tells you the capacity. And as n goes up, the capacity goes up. Okay, so guys, that's energy levels. But here's the thing. Bohr knew all of this stuff. This is the Bohr model of the atom. This is what Bohr discovered by studying light. But again, it wasn't right because the electrons are not in paths. They are in clouds. They're in energy levels, and those clouds don't all have the same shape. So then they included the sublevel number, and the sublevel number L tells us the shape. You'll notice I didn't put a blank for shape. You can write it in. Just put a dash and then the word shape. Now, how many different shapes, how many different sublevels can be in an energy level? And the answer is n. You'll notice there's 2 blanks to fill in. The number of sublevels in an energy level is n. And so now you're saying to yourself, what on earth does that mean? Guys, watch my fingers. You ready? Energy level 1 can have how many sublevels? 1. Energy level 2 can have 2. Energy level 3 can have 3. Do you understand the pattern? Energy level 4 can have 4 sublevels, 5 can have 5, and so on. So the number of sublevels that an energy level can have is the number of the energy level. But guys, here's the thing. These sublevels, these shapes have names. And guys, we're about to tickle your brain a little bit, because what I'm about to share with you, you heard before. And you're going to go, oh, I remember SP, D, and F? Remember that? Remember that? You saw that in the video. We saw S, and we saw P, and we saw D, and we saw F. We saw that in repeated points in the video. I didn't expect you to understand it then. I don't expect you to understand it now. I just want you to understand you've been exposed to this before. S, P, D, and F, guys, are the names that we give to the sublevels. So now let's tie the pieces together. You ready? See if you understand. First energy level has how many sublevels? 1. It's an S. The second energy level has how many sublevels? 2. S and P. The third energy level has how many sublevels? 3. S, P, D. The fourth energy level has how many sublevels? 4. S, P, D, and F. The fifth energy level has how many sublevels? 5. S, P, D, F, G. Now guys, here's the trick. We do not have atoms in our universe that are complex enough to need a G sublevel. We've done the math, we've graphed them. If you want to know what they look like, you can Google it. Guys, we know what the G sublevel should look like, but we don't have atoms that are complex enough to need it, so we don't talk about it. So here's what we say. It goes S, SP, SPD, SPDF, and then for energy levels 5, 6, and 7, we just say that those are SPDF as well, because we don't need the G, H, and I, because we don't have atoms that complex. Okay, so now sublevels are broken down into orbitals. The orbital quantum number then, guys, tells us the orientation of the orbital, up and down, left and right, in and out. We'll talk more about it later. But, guys, here's the thing that you need to know about orbitals. And maybe you caught this in the videos. How many electrons can go in an orbital? 2. So, guys, an orbital is the space that is occupied by 2 electrons. But now, guys, we've got a problem. Do you see the problem? What's the problem with orbitals? Well, let's think about it. So, guys, how many electrons can go in an orbital? 2. What's the charge of this electron? Negative. What's the charge of this electron? Negative. And what do they do in an orbital? Pair up. What's wrong with that? They're both negative. Do they want to pair up? They want to repel. So guys, this was a major problem with this idea until they found out something really cool about electrons. Because guys, electrons pair up in an orbital, and they don't want to pair up in an orbital. So how is it that electrons can pair up in an orbital? You ready for this? This is crazy. Guys, electrons are actually like little Earths. Follow the thought. So guys, if you think about the Earth that we are standing on, there's a North Pole and there's a South Pole. And those are magnetic poles, right? And so our Earth spins around its magnetic pole with the North Pole on top and the South Pole on the bottom. Got it? Okay, Matt, don't miss this. This is, and maybe you already understand this, but make sure you catch this. So the idea here, guys, is that you understand that our globe has a North Pole and a South Pole, and it spins like this. Electrons are the same way. Electrons have a North Pole, and electrons have a South Pole, and electrons spin. So here's what happens. See if I can do this. Oh boy. Okay, so we've got these 2 electrons, and my fingers are pointing towards the North Pole. I feel like I'm hula hooping. So we've got these 2 electrons, and they're both pointing towards the North Pole, and they're both spinning in the same direction. And when they go to pair up in an orbital, one of them flips over. So now they're spinning in opposite directions. But their spinning in opposite directions tells us what about their poles? One north pole is pointing up and one north pole is pointing down. And what will that do to them if one is north pole up and the other is north pole down? Makes them attract. And that attraction overcomes the repulsion between the negatives and it allows them to pair up. Crazy, right? So here's the thought. This last number, the spin quantum number, explains the fact that in order for electrons to pair up in an orbital, they must have opposite spins. I'm going to change that. They must have opposite, what does your paper say? Does it say something down there? Because maybe they must have, I'm going to change this, opposite magnetic poles. That's better. That describes it better. They must have opposite magnetic poles. So what we do, guys, is we describe the spin number as up and down. Spin up has a value of +1/2 in Schrodinger's equation. Spin down has a value of -1/2 in Schrodinger's equation. All right, so now you're saying to yourself, good stinking night. That was a pant load of material. What on earth am I supposed to know? Well, guys, bottom line is this. This is what you're supposed to know. Grab it. This is your homework. Do not make the mistake of doing this Sunday night. You will remember 0 of this. So, guys, here's your goal. Get this done right now. Cement your understandings before they leave you. But guys, with that said, I'd like you to look at the last question with me, please. Let's do the last question together. There's a problem with it. Question says this: what is an orbital? Please don't write any of these things down. Just listen. You'll know, and you can write it down later. What is an orbital? The space that 2 electrons occupy. Sorry, that's the second question. What is an orbital? It is the cloud that is occupied by electrons. How many electrons can each orbital hold? 2. What has to be true of the electrons that are in the same orbital? What's the answer? What has to be true? They have to have opposite spins. Now, guys, read the last question. This is bad. It says, why do we use this term, opposite spin? Why do we use the term opposite spin if these electrons aren't actually spinning? And you're going, wait a minute, Amber just said the electrons are actually spinning. Guys, they are actually spinning. So let me explain to you what happened. In years past, we didn't think our students were smart enough to understand electron spin. Okay? Here's why electron spin is a problem. If an electron spins, what does it have to be? A particle, right? Waves don't spin. So if electrons spin, they have to be particles. And students have struggled with this because the entire Schrodinger model of the atom is based upon electrons being what? Not particles, but waves. So what's the deal? So what we've done in the past is we've just told students electrons are waves, they are particles, and therefore spin makes no sense. We think you guys can handle it. So what's the truth? Is an electron a wave that looks like a cloud, or is an electron a particle that spins? The answer is yes. It's both. When you study an electron like a wave, it fully behaves as a wave and a cloud and an orbital. And when an electron is a particle, it spins and has mass and does all the other particles do. It's both. And it makes no sense. But it's true. So guys, electrons actually do spin because they really are particles, and that doesn't disprove anything about them being waves and clouds. So we're going to get rid of that last question and we're going to change it. You ready? So that last question, the very last question, why do we use the word spin if they really don't spin? Cross it out. And here's the question we're going to replace it with. What does the spin tell us about an electron? So can we just answer that right now? What does the spin tell us about an electron? The direction of what? The North Pole. So guys, the spin tells us the direction that the North Pole is pointing. So, guys, I would say flip this thing over. You've got 15 minutes. Hey, all of you are in Pride, because we're basing Pride on first quarter's grades, and we all got it. Nice work. Not even a single NC in this class. I don't think I've ever had that happen. Not that you're like my students, but it's kind of cool. So nice job, y'all. So we're all out for Pride. But guys, seriously, the next 15 minutes, get this done. The answers are on the wall. Get all this done so that you don't forget. Yeah? Yeah? Oh, hold on. Let me stop recording.